All right, everyone. It is 1 p.m. Eastern time, so let's go ahead and get started. Welcome to the third talk of Monte Carlo week for the third week of this 2025 MTV Nuclear Engineering Summer School, or MTV NESS for short. Today we will have Alex Tuckey. Alex Tuckey is an incoming nuclear engineering master's student at the University of Michigan. He completed his undergraduate degree in physics, also at the University of Michigan. His current work focuses on determining the optimal parameter values for the Frey fission model, which will be the focus of today, for neutron-induced fission. Today, Alex will be presenting on simulating fission events with Frey. Take it away, Alex.
Yeah, thanks, Glenn, for that introduction. So the outline of today's lecture is going to be as follows. We'll first start with an overview of some fission nomenclature. Then I'll introduce the fission model Freya that I work with and will broadly be the topic of today's lecture. Next, I'll go over briefly how Freya works and walk through an event generation. Then we'll spend the bulk of the talk discussing the Freya parameters. And finally, we'll conclude with a live demo of running Freya and going over the output file. So the two types of fission we're going to be concerned with today are spontaneous fission and neutron-induced fission. In spontaneous fission, the internal excitation energy of the nucleus is high enough for it to fission without any external energy applied, whereas neutron-induced fission requires an incident neutron of sufficiently high energy to overcome the fission barrier of the target nucleus. And so we refer to the composite system of the incident neutron and the target nucleus as the compound nucleus. And I have this animation here on the right that can be interpreted as either spontaneous fission or neutron-induced fission starting from the compound nucleus. And so once our incident neutron is absorbed by the target nucleus, in the case of neutron-induced fission, the compound nucleus begins to split into two distinct fragments. As you can see from the animation, there's kind of this peanut shape that evolves. And once the prefragments snap, that's referred to as scission. And in our case today, we're going to only be concerned with binary fission, in which the nucleus splits into two fragments. There's also ternary fission, in which there's three fragments, but unfortunately, Freya doesn't model that currently, so we'll be focusing on binary fission. And there's two kind of subcategories of binary fission, which will be relevant today. The first is symmetric fission, in which the two fragments are near equal mass. The other being asymmetric fission, where we have a light fragment and a heavy fragment. So these fragments that I've just mentioned are highly excited after scission, and by conservation of mass and charge, the masses and charges of the light and heavy fragments have to sum to the mass and charge of the compound nucleus, respectively. So these two fission fragments in binary fission are highly excited, and they de-excitate in two stages, the first being prompt emission and then delayed emission following that. So we refer to the fission products as the result of the fragments after prompt emission. And then after both prompt and delayed emission, we call those cumulative products. So prompt emission happens first, typically within the first 10 to the minus seconds, in which we have neutrons first emitted, and then that's followed by photon emission. And importantly, during prompt emission, only the mass of the fragments change, and specifically they're reduced since we are emitting neutrons, and the charge of these fragments remains the same. Delayed emission occurs following prompt emission. We still emit neutrons and photons, but there can be delayed processes like beta decay in this stage, in which a neutron turns into a proton, electron, and electron neutrino. So that means during delayed emission, the charge of our fragments can change, specifically increase, since we are turning a neutral charge into a positive charge in the nucleus of these fragments. And again, the mass of the fragments is further reduced by neutron emission during the delayed emission stage. So there's two other neutron emission processes that will be relevant for my talk. And both of these are in regards to neutron-induced fission. And both of these may occur and may only occur before scission occurs. So the first of which that I will discuss briefly is pre-equilibrium emission, in which our incident neutron is absorbed by the target nucleus, creating that compound nucleus, but it doesn't fully equilibrate, and so it's re-emitted again. In that case, if the excitation energy of the excited nucleus is above the fission barrier, it can go on to fission. If not, it doesn't. The second type of neutron emission that can occur before fission is what's called multi-chance fission. This is somewhat similar to pre-equilibrium emission, except that our incident neutron is fully absorbed by the target nucleus and comes into equilibrium with it. Now, when this happens, the excitation energy of the compound nucleus can be above the neutron separation energy, which I'll explain shortly here. And if that's the case, then a neutron can be emitted. And if the resulting excitation energy of the nucleus is still above the fission barrier, it can go on to fission. In that case, that's what we refer to as second chance fission, since we emitted one neutron and then went on to fission. You can imagine a scenario where we emit two neutrons and then go on to fission. That's what's referred to as third chance fission, and so on. I have one more slide of nomenclature here, just bear with me. This will be relevant for the rest of the talk. The fission Q value consists of the total energy released in fission, and this is divided between the total kinetic energy and total excitation energy of the fission fragments. This total excitation energy is further subdivided into the intrinsic excitation energy and rotational energy of the fragments. And so during our emission processes, we dissipate this excitation energy. The intrinsic excitation energy is dissipated by neutron emission during the prompt emission stage, just mentioned previously. And then our rotational energy of the fragments is associated with their spinning, and that is dissipated by photon emission. So I have this diagram on the right here, walking through the prompt emission of a fission fragment, which is in this gray blob. And so while the excitation energy of this fission fragment is above the neutron separation energy, we emit neutrons. And this neutron separation energy is simply the energy needed to remove one neutron from the nucleus of the fragment. So we emit neutrons while we have enough energy to do so, while our excitation energy is above the neutron separation energy. Once we drop below that point, we then emit photons. And so first, in the photon emission, we have what are called statistical photons. And these are emitted from a continuous energy spectrum, and they have very little effect on the spin of the fission fragment. Following statistical emission, we have these discrete transitions, which are referred to as YRAS photons. These do significantly reduce the spin of the fission fragment, and this photon emission occurs until the fragment is no longer in an excited state. There's two other quantities on the slide that I haven't touched on yet, so just briefly, the neutron multiplicity and photon multiplicity are simply the number of neutrons and photons, respectively, per fission event. Okay, so now I can introduce the fission model FRIA that I work with. FRIA stands for the Fission Reaction Event Yield Algorithm, and it's been being developed by Mona Vogt at Lawrence Livermore National Lab, UC Davis, and Jeroen Randrup at Lawrence Berkeley National Lab to study event-by-event fission. This is a publicly available fission model. I'll go ahead and post the link to the source code and documentation at the end of this lecture, so you can give it a try for yourself afterwards. And Ramona and Jeroen put a large emphasis on speed so that we can generate complete fission events very quickly, large samples of them. So FRIA currently only models fission through prompt emission, giving us our fission product yields. But there is work being done to include delayed emission processes like beta decays. And this would give us our cumulative product yields. But this is an unreleased version, so still for the future. You're probably wondering what this picture is I have here up on the slide. This is the Norse goddess Freya being pulled in her chariots of cats. I think it's funny to think of this picture every time I run the code. Okay, so FRIA isn't the only complete event treatment out there, and there's also more traditional fission models that exist. But these two complete event treatments and traditional fission models differ in a very important way. So in these more average fission models, fission is treated like a black box where we're only told the neutron multiplicity and gamma multiplicity. There's really no information on the particle correlations or the kinematic correlations between the fragments or the particles themselves. Additionally, energy and momentum aren't conserved in these models. Well, ultimately, these correlations throughout the fission process can't be addressed. That's a large disadvantage. We have models like FRIA, which perform complete event treatments. And these models do conserve energy and momentum. And FRIA specifically outputs the energy and momentum of the neutrons, photons, and fission products in each individual fission event. This allows us to address the correlations throughout the fission process. And so, this is useful because we can use these codes to study different sensitivities of fission observables and therefore help inform which measurements to take in the future. I did see a few raised hands. I'd just like to remind everyone to use the Q&A feature if you do have a question. So now I'll briefly go over how FRIA works and walk you guys through an event generation. So first, we have to specify the charge, mass, and energy of our target nucleus. Currently, FRIA supports these 6 spontaneously fissioning nuclei and these 5 neutron-induced fissioning nuclei up to 20 MeV. There is the potential to include photofission, which is another type of induced fission, but it's caused by a photon instead of a neutron. But that is also work for the future. But anyways, once we have specified the charge, mass, and energy. Freya moves forward and selects the charge and mass of a fragment from data where it's available, or if it's not, it uses a model's prediction. So far we have specified the target nucleus and we have a single fragment. We obtain the second fragment simply by mass and charge conservation, since we cannot lose mass or charge during this fission process. So now we have the light and heavy fragment, which allows us to obtain the total energy released in the fission process. And this is a product of E equals mc squared from Einstein. So the mass difference between the compound nucleus and our two fragments is equal to the total energy released. And this total energy released is both the kinetic energy of the fragments and the excitation energy of them. And so we have to again sample from data here to get the total kinetic energy. And then the total excitation energy is readily determined by energy conservation. This total excitation energy is then divided between the fragments for both their intrinsic excitation energy and rotational energy. At this point, we consider free equilibrium emission and multi-chance fission if we're dealing with neutron-induced fission. Afterwards, the rest of the event generation has to deal with the prompt emission of the fragments. So we're first de-excitating by neutron emission until that excitation energy of the fragments is below the neutron separation energy. And following that, we have photon emission, which first is statistical and then moves to discrete transitions. And this photon emission occurs until the fragments are no longer excited. So I want to point out that, or really emphasize that there's points during this process where we have to draw from data. Unfortunately, there's not a complete theory of fission currently that I know of. So we kind of have to do our best with these phenomenological models like Freya. Maybe one day, if we get a complete theory of fission, we can work from first principles. But this is what we've got for now. Okay, so what I just described was for one event, but we want to do this many times because Freya is very fast and we want more statistics. So Freya is very good at this, at generating these large samples of complete fission events very quickly. And the output of these events contains the kinematic information of the fission fragments and the prompt neutrons and photons. And so from this output, we can extract various correlated fission observables, as I hinted at before. So here on the slide, I've chosen to focus on the average neutron multiplicity, which I have as functions of fragment mass and total kinetic energy. If we look at the plot on the left first, we see this sort of sawtooth shape in the neutron multiplicity, where the light fragment typically emits more photons than the heavy fragment, or excuse me, neutrons than the heavy fragment. And we see this dip around a fragment mass of 132. And if you recall to, I believe this was mentioned in an earlier lecture in the summer school, the shell effects that become present when we have these magic numbers of nucleons. So this fragment mass of 132 corresponds to tin 132, which has 82 neutrons and 50 protons. And so that forms a closed shell in the nucleus, meaning it's more stable than it would be otherwise. So that's why we see this reduced neutron emission around this fragment mass of 132. Switching over to nu bar as a function of TKE, we see this negative trend. And this can be explained by the fact that the total energy released in fission is this balance between the TKE and the TXE. And so if we're increasing the kinetic energy, that means we're taking away from the total excitation energy. And it's this excitation energy that's available for neutron emission. So therefore, we have less neutrons emitted at these higher kinetic energies. So Freya has 5 physics-based parameters that need to be specified to generate any output. The first of which, E0, is related to the excitation energy at scission, which I have denoted here ECS, or sorry, SC. And E0 determines the scission temperature, which essentially determines how excited the fragments are. And this excitation energy at scission is divided into the rotational energy of the fragments and the statistical excitation energy of the fragments, which I had previously referred to as the intrinsic excitation, but it's the same thing here. And so it's in this statistical excitation energy that our second parameter x comes into play. Initially, we divide the statistical excitation energy into or between the light and heavy fragments according to something called their level densities. But since we know from measurement that the light fragment typically emits more neutrons on average than the heavy fragment, we enhance the excitation energy of our light fragment by this parameter x, where x is greater than 1, in order to give it that higher neutron emission that we saw in the sawtooth previously. So we have to maintain energy conservation. So we subtract this enhanced excitation energy from the total excitation energy, and that excess is then given to the heavy fragment. Our third parameter is also related to the excitation energy of the fragments. These fragments have thermal fluctuations around the mean value of their statistical excitation energy. And this thermal variance in Freya is drawn from a normal distribution with variance shown here in bold, which is determined by the C parameter. So you can think of C as controlling the maximum excitation energy of the fragments. And again, we have to maintain energy conservation. So these thermal fluctuations that we add to both the light and heavy fragment, we subtract from the average total kinetic energy. Our fourth parameter, CS, is related to really all of the photon observables because it determines the spin fluctuations around their mean value. So these fragments are spinning when after scission, and the magnitude of their spin fluctuates from their mean value, and CS determines the relative degree of these fluctuations, which is proportional to the scission temperature. And finally, our fifth parameter, DTKE, is sort of this wildcard parameter where we use it to shift the average total kinetic energy in order to reproduce a measured value of the average neutron multiplicity. And we do this because we sample from data to obtain the total kinetic energy. And this data can have unquantified uncertainties or, in some cases, low statistics. So this DTKE parameter is introduced to compensate for that. And you might imagine that since these parameters are defined in relation to physical quantities, that they would correspond to various fission observables, and you'd be correct. So let's first focus on E0 on the left here. I've plotted the prompt fission neutron spectrum for various values of E0. And we see that for the smallest value of E0 in red, the PFNS becomes softer, meaning that there's a higher probability to emit these low energy neutrons. And this makes sense because for a smaller value of E0, we have a smaller scission temperature from the relation showed on the previous slide. And so these fragments are less excited and therefore tend to emit neutrons of a lower energy. And I would like to note that really all of the parameters affect the prompt fission neutron spectrum, but the prompt fission neutron spectrum is the only observable that E0 has a noticeable effect on. So we attribute E0 to this observable. In the middle plot here, I have the average neutron multiplicity as a function of fragment mass for different values of the X parameter. And you'll see that for increasing values of X, if we focus on the green points here first, the sawtooth behavior of this distribution is amplified, meaning that there's a greater difference between the number of neutrons emitted by the light fragment and heavy fragment. Conversely, if we reduce X to below 1, now we're giving more of the excitation energy to the heavy fragment. And so it now emits more neutrons on average than the light fragment, creating this kind of a more linear trend in red. And then finally on the slide here, the C parameter determines the width of the neutron multiplicity distribution. So for smaller values of C, we are perturbing the average excitation energy of the fragments by a smaller amount. And so they have less energy available for neutron emission. And so they'll emit less neutrons on average. And you can just flip around what I said for large values of C to explain why the distribution becomes wider. I just want to briefly touch on the last two Frye parameters and the fission observables they correspond to. These are a little bit different than the rest because they primarily affect single valued observables as opposed to those correlated fission observables in the last slide. As I hinted at before, the CS parameter primarily has to do with photon emission. And we see this positive correlation between the average photon multiplicity and the C parameter. This can be explained by the fact that when we increase our C parameter, we are increasing the spin fluctuations. So we're giving the fragments a higher spin with these increased C values. And to dissipate the spin, these fragments have to emit a higher number of photons. Finally, the fifth Frye parameter, as you probably would have guessed, is directly correlated with nu bar. And so as we increase the total kinetic energy given to the fragments, we have to take away from the total excitation energy, meaning we have less energy available for neutron emission. Very similar to the trend we saw in the average neutron multiplicity as a function of the total kinetic energy of the fragments. So you're probably wondering how we determine um, the right values for these parameters, so to speak, because we can't just arbitrarily choose them since, as we've just seen, they have very pronounced effects on the resulting fission observables extracted from Freya. And the method that has been developed in the past and the method that I am drawing from in my work is to choose the parameters that best represent um, current data for a given nucleus. And so this was done in a work by Jackson Van Dyke, Lee Bernstein, and Ramona Vogt back in 2019 for the spontaneously fissioning nuclei in Freya. This chi-squared minimization that I have on the slide just refers to the fact that we are choosing the Freya parameter set that best reproduces data we feed into the optimization. And they chose to optimize the Freya parameters based on the simulated annealing method. And so they fed in data like these on the slide, in addition to more neutron observables and photon observables as well. And, you know, if we can reproduce current data with Freya, that's great. But ultimately, the goal is to use Freya to make predictions for where data is lacking or entirely missing. So the idea here is that by tuning the Freya parameters to currently existing data, we improve its predictive capabilities. Here are all of the optimized parameter values and their uncertainties for the spontaneously fissioning nuclei in Freya. I'm not going to go through all of them here. It'll be kind of a lot, but I will remark that the quality of the fit and the level of constrainment of the Freya parameters is based on the amount of data that we feed into any optimization, since the data is what we're using as a benchmark. So for a nucleus like Californium, where we have 4 data sets and 2 evaluations, the Freya parameters are better constrained than, say, in the case of plutonium-238, where we only had 1 evaluation to work with. So I am currently working on a similar optimization, but for neutron-induced fission. So this would be the first attempt to capture the energy dependence of the Freya parameters. And I'm adopting a similar chi-square minimization as kind of my metric, but instead I'm using a genetic algorithm as opposed to the simulated annealing method used for spontaneous fission. I can get into the reasons for that after this talk if anyone would like, but gonna save that for the end necessary. So I have some preliminary results of this optimization on the slide here. On the left, we see a positive correlation between the CS parameter and the incident neutron energy for plutonium-239. And we sort of expect this intuitively from a physics standpoint, because as we increase the incident neutron energy, we are increasing the excitation energy of the fragments and therefore their spin. And so since CS is this, determines the spin fluctuations, an increase in CS gives the fragments more spin. And this spin has to be dissipated through photon emission. So we can kind of translate this over to its corresponding fission observable, which is the average photon multiplicity shown on the right here. And this is as a function of incident neutron energy. We see an overall increase because we're left with more excitation energy in the fragments after neutron emission occurs. So that still has to be dissipated. And so that's, afterwards photon emission takes over and de-excitates them fully. And yeah, this is still a preliminary result, but you can see that as a result of this optimization, using the genetic algorithm, we're getting some pretty nice agreement between the data by Nathan Giha and the Fry result. Okay, it looks like I'm doing pretty good on time, so that's good. I'll just wrap up by making a few concluding remarks and then switching over to the demo I promised at the beginning. So fission is a very complicated process, and it's not completely described by theory. And so we rely on codes like Freya to model complete fission events in order to address these correlations throughout the fission process. And the best we have to work with at the moment are these phenomenological models because we don't have a complete theory of fission. And so because of that, we have to continuously update these models in order to incorporate new data. And that's what I was trying to explain with the Freya parameter optimization. As we get more or better data, we need to adjust the model parameters accordingly. So again, here is the link to Freya source code and documentation. I can go ahead and post this in the chat now really quickly. So there you go, you have that. So you can play with Freya after this live demo, which I'm going to go ahead and switch screens here. Okay, can you see my terminal okay, Flynn?
Yeah, looks good, Alex.
Okay, sweet. So if you click on that link I just provided, takes you to the Lawrence Livermore National Laboratory website. You can download Freya source code. It has installation instructions with the giant zip file you're gonna download. And it's really a pretty straightforward and simple download installation. It only took me about a few minutes. But I'm not going to walk through this process, just for the sake of time here. But when you download the source code, it's going to be in a directory named something like fission _ v 2.0 point something or something like that. And I've just renamed that directory here to Freya. So just want to avoid any confusion there with that. So I guess I'll first show you where these Freya parameters I've been talking about are specified. So there's a directory called data Freya, which houses, as you might imagine, all the data that Freya draws from, including the input parameters. So those are located in this input parameters.dat file. And so here are housed all of the Freya parameters for all of the currently supported nuclei, both spontaneously fissioning and neutron-induced fissioning nuclei. I'll mention that what I've referred to as E0 is this A level 0 parameter. This X epsilon is X C is the same, CS is the same, and TTK is the same. These other two entries are related to, well, this first one, Gmin, is related to photon emission, specific to a detector used in an experiment. So this doesn't have any effect on the Frye output directly. And these DTK files are where the total kinetic energy is drawn from for neutron-induced fission. Okay, so you can change these values if you want and see how that affects the Frye output. It's kind of, I hope I've given a good overview of that already. But let's go ahead and exit out of here and now actually run Frye. So we'll go back to the main Frye directory, and there's this executable called recipe. So let's go ahead and run that. Okay, it's now asking us for the charge of our target nucleus. So why don't we do plutonium-239 neutron-induced fission. So that has charge of 94, mass 239. We can do a large instant neutron energy to see some of the pre-fission neutron emission. So do 15 MeV there. And just to be quick, do 100,000 events. Let's see, we can name our output file plutonium-239 neutron-induced fission. So now Frye is running at the inputs we specified. Sure, want to take a second, and yep, just like that, we have 100,000 events generated for plutonium-239. So we can go through the output file really quick and see what that contains. It says our events were dropped off in this directory. Let's head there, and we can look for the output file we just named. Very large, that is okay. Okay, so this is what the Frye output file looks like. The header line here contains the information for the compound nucleus. So we did neutron-induced fission of plutonium-239, meaning +1 to get our compound nucleus of 240. Our incident neutron energy was 15 MeV, and we simulated 100,000 events. The rest of the output file is in this repeated structure, where each event is broken down into 3 sections. There's one section for the fissioning nucleus, one for the light fragment, and one for the heavy fragment. I can walk through that structure here. So our first event is specified by this one in the beginning of the line, and it continues down all the way until the 2 for the second event. Let's see if I can highlight this. Okay. So this is the first section of the first event, which contains the information for the fissioning nucleus. Let's see, we had plutonium-239 neutron-induced fission. Our charge remained the same at 94 as expected, but the fissioning nucleus was a mass of 239, which means we must have emitted a neutron pre-fission. And if we look right here, this 1 means we did in fact emit a neutron pre-fission, and we had 0 gammas or photons emitted before fission. So next, this line directly under the fissioning nucleus information, or line, I should say, is the energy and momentum of the fissioning nucleus. So it had an excitation energy of 0.069 MeV. excuse me, that's the kinematic or the kinetic energy. And the last three digits here are the momentum unit vector of the fissioning nucleus. The last part of this section is the energy and momentum of the pre-fission neutron that was emitted. It had kinetic energy of 3.215 MeV, and this is its momentum unit vector. We did not have any gammas emitted prior to fission, so we don't have any gamma lines for this section of the event. The rest of the event follows the same structure, so I won't repeat myself too much. But we know this is part of the first event still because of the one that is at the beginning of this line. Our light fragment had a charge of 43, a mass of 111. We had 2 prompt neutrons and 3 prompt gammas coming from the light fragment. So again, energy, momentum of the light fragment, energy and momentum of our 2 prompt neutrons. And then in this case, we did have gammas or photons. So here's the energy and momentum of those 3 photons. And as you can guess by now, the heavy fragment has the same structure as the light fragment and fissioning nucleus. Interestingly, we had no neutrons emitted from the heavy fragment, but 9 photons. Yeah, so okay. The same structure is repeated for the rest of the events in the file. So there's several hundred thousands of lines here. And unfortunately, Fire doesn't come with its own parsing script. So you'll have to write your own. I guess I'll give that to you all as homework. And I've actually found that the parsing time, at least my parsing script, takes much longer than the event generation time. So if you're able to write a parsing script that is comparable to the event generation time, please let me know. I would recommend maybe starting by extracting a single valued observable like new bar, and then trying something more complicated and interesting like new bar as a function of fragment mass to get the correlated fission data that Fry is really all about. Okay, so I can switch back over to a PowerPoint here. Just to say thank you all for listening, for your time and attention. And I'm happy to take any questions you guys might have at this point.
Thanks, Alex. Nice talk and nice demo. I definitely learned a bit more about those Fry parameters, have a nice understanding now, and it's nice to see how easy the program is to run. I have a couple of comments and questions, and then we got a few in the chat and the Q&A. My first one being, you showed that when you generated that output and did your compilation, you could enter a single energy, right? You did 15 MeV, I believe, on the example. Is there an option for a continuous energy input?
Like 15.1 MeV, for example.
No, instead of like a single value, right?
Oh, I see.
You could run the same code, but it's got, a sampled source, right? So you're starting to get to an actual transport simulation, or is that not built into Fry? You'd be pairing it with a software.
Yeah, unfortunately, that's not included in the standard package. You'd have to write something externally that feeds in energies or samples from a distribution, feeds those energies in to Freya. Yeah, that unfortunately it doesn't work like that.
Yeah, then my other one was more of a comment than a question, but it looked like this code's compiled in C++, right? So that probably helps a lot with the speed. When you're post-processing, are you using Python or what type of scripts have you implemented?
I'm entirely using Python,
Mhm.
just because that's what I'm most familiar with. Um, I really haven't dealt with this Fry source code much at all. Um, you know, it runs fine as it is. If you want it to output more information, then you could dive into the source code, which is in C++, as you mentioned, and also Fortran. Um, I don't know if anybody these days actually knows that, but um, it can output more information. But the the parsing scripts I use are in Python, um, and yeah, that works fine for me.
Yeah, that's interesting. I'd be interested in talking to you another time about the parsing scripts. I think it'd be a task to do your own parsing in C++, but if that's what takes most of the time in the Python, you could, have a, I suppose, more formatted or uh, better packaged output, right, that you could create with Fry for your purposes. But anyway, we should get on to the Q&A. So we've got quite a few here. Some were very specific to the slides, but I saw some general ones. I'll hit you with the first, I think, most general one, which is kind of along the lines of what we were talking about. Um, One of our attendees asked, can you integrate Fry into um, Monte Carlo codes like MCMP and JAT4 and use it for your source generation?
Yeah, you certainly can, and that's one of the things it was intended to do when it was designed. I unfortunately don't have much experience with that, so I can't really um, comment much more on that other than yes, you can. Um, so sorry, I wish I could go into more detail on that.
Yeah, and Alex, I'll just take the liberty to add to that. The newest version, MCMP 6.3, is actually shipped with Frya. So these fission event generation softwares are built into some of the latest MCMP codes. As far as JANT4, I haven't seen an implementation, but with JANT4 being a C++ code, I'm sure it would be reasonable to couple uh, those packages. But yeah, thanks, Alex. Let's see. Pick my next favorite here. Um, yeah, so I think very early in the slides, so you're going to be going back now to like 6 and 7. Um, Somebody asked, why are we ignoring trinary fission? Under what rare conditions might we consider trinary fission?
Um, well, I simply didn't discuss uh, trinary or ternary fission here
Mhm.
because Freya doesn't support the modeling of that. Um, it certainly can happen, but from my understanding, it's a much more unlikely process than binary fission. Um, but yeah, I just left it out because Freya doesn't currently support that.
Thanks, Alex. Let's see. Does Fry consider a variable for the angle of the fission products or neutrons, relative to each other?
So that can be extracted from the output based on the momentum vectors. If that's what you're referring to, um, I don't know if that question more means the angle of the incident neutron coming into the target nucleus. Um, but from my understanding, there you can't specify, the angle of the incident neutron, um, and I don't believe that that would have much of an effect on the output, anyways, since it's symmetric based on which way you look at the system.
Yeah, Alex, I think you answered that well. And I think they were more concerned with the outputs of fission products and neutrons. But to kind of rephrase what you just said, sounds like all the outputs are based off the center of mass frame of reference, right? So it all depends on your frame of reference, but I believe this is all center of mass. Is that correct?
Yeah. Yep.
Thanks. And I see a raised hand. We will not be calling on raised hands. Sorry, we do not have the time, but feel free to put your questions in the Q&A. Our apologies, we can't get to all questions, but we should continue on. Somebody's asking very generally, notable research trends or published studies that have leveraged Freya. I think you alluded to a few in this talk, particularly those considering like prompt fission product yields, beta delayed emissions, high-speed simulation methodologies. Can you recommend some works?
So there's a bunch of papers by Ramona and Jörn on comparing the Freya output to currently available experimental data. I would recommend just looking these two up on like Google Scholar or something, and I'm sure you can have a deep dive there into that. There's also this paper I just mentioned before, which optimized the Freya parameters for spontaneous fission. So yeah, there's also that as well. Those are, sorry, I don't have a better answer to that. Kind of blanking right now, but those are
Not,
the
I think you gave a nice answer, but yeah, you're showing a few publications here like Santi and Miller, Dushin and Gook, right? That are measurements that you're comparing to, but I think these are plots that you generated, but these have been compared to before, right? With Freya?
these are actually taken from the publication on spontaneous fission.
Nice, nice. So yeah, so this isn't a published work, and yeah, I think that's more what they're looking for. But yep, just come back to Alex's slides. You should be able to find them all. Let's see, getting a little low on time, but we're gonna do a couple of questions here at the top. Going back to slide 6 and 7, start with slide 6. Can you explain what you mean, like just recontextualize the neutron-neutron, neutron-gamma, gamma-gamma, and kinematic correlation? So what's the physical meaning there?
So for the particle correlations, when we talk about neutron-neutron correlations, for example, that could be the angle between two emitted neutrons, or well, primarily, yeah, that's what I had in mind, is the angle between neutrons emitted from the same fragment. And you can apply that to neutron photon correlations or photon photon correlations. The kinematic correlations can be, for example, what I showed here, the plot on the right. The neutron multiplicity is a function of the total kinetic energy of the fragments. Or you could, there's all sorts of ways to mix these different fission observables. So you could have like the angle of neutron emission as a function of the kinetic energy of the fragments, for example.
Yeah, that makes sense. Thank you, Alex. Going back to slide 7, you mentioned the total excitation energy being divided into this static and rotational energy. What models, under the hood actually determine this distribution for these isotopes that fission?
That's a good question. I don't have much experience with the Freya source code, so unfortunately, I can't go into much detail on that. But I will say the link that I provided for the documentation and source code itself, that will walk you through this event generation as well. And if they don't go over the specific models in that document, there's references to the papers that explain that.
Cool, thanks, Alex. And then I think we've got time for one last one. When you go to slide 10, they're asking, we can see the lower fragment mass number, the higher the error bars, right, on this new bar term. This attendee is just asking, why is that? Is there a reason for this experimentally, physically?
Great observation. So these error bars I'm showing here are purely statistical error. So at these lower fragment masses, we have less counts per bin because it's just less likely to get fragments at the tail ends of the distribution. So the statistical uncertainty is proportional to the amount of counts we have per bin. Or inversely proportional. I might have said that incorrectly, but point being, we have less statistics in these lower bins, and so we're more uncertain on the Fryer result. I only ran this plot for 100,000 events just because I wanted something extremely quick to get on the slide. But if you run, say, 1,000,000 events, which takes only about a minute, these statistical error bars are essentially non-existent.
Cool. Thank you, Alex. I think that's time for all the questions today. Thank you once again, Alex, for your great talk and demonstration. Next week, we will be back on Tuesday, and we will be going over radiation imaging. So radiation imaging week, and we'll have 3 speakers, 2 students to start the week off, and a guest speaker from Oak Ridge at the end of the week. Please plan to join 1 to 2 p.m. Eastern, Tuesday through Thursday. Thank you again, Alex, and we'll see you all.